Hello, everybody. Rich here. I'm going to be going through a couple of things about Lab 1. We've had a few lab sessions now, and I've talked to most of you, but I think there are some general misconceptions about what the lab is asking us to do and how to go about doing it. So I wanted to try and explain some of that. Okay, so the first thing I'm going to do is I'm just going to go to the lab handout and kind of skim through it, pointing out some important details. So the first thing here in section 1, we are asked to design a circuit that takes 3 inputs, and they're called word level inputs: A1:0, B1:0, I1:0, where A, B, and I are each 2-bit vectors. So what that means is that we'll be designing a circuit that takes an input, well, 3 inputs, just like it says, and each one of those inputs consists of 2 bits. So A would be anything between 0 and 3 that in binary, right? So 0, 0, 0, 1, 1, 0, 1, 1. And B and I the same. So those are our potential values for A, B, and I. And then we're told that and then we're told that the values of the I think I missed a step. Here we go. Okay, yeah. We're told that the output will also be a 2-bit vector. We'll call it F. And so the circuit looks something like this. We have A, B, and then I, and then an output F. Depending on what I is, we do different things to A and B. So what we're building here is basically like an ALU, an arithmetic logic unit, or like a very simple computer.
So, Dad, why are
So yeah, so we're gonna basically have to figure out, first of all, what do we need to do with A and B, depending on the value for I, and then the second thing is how do we make a choice in hardware. So let's start with, we're given what I needs to be, or rather we're given what the instructions that I represents. So if I is 0, 0, then the output for F is an ANDing of the inputs A and B. When I is 1, 0, or sorry, rather, when I is 0, 1, the output is an ORing of the inputs A and B. When I is, where is it? 1, 0, there we go. When I is 1, 0, it's an equality check. And when I is 1, 1, it's a complement. So let's go ahead and start by writing that out. Now, I saw a lot of people in the labs trying to do something like this, where they had I0, I1, A0, A1, B0, B1, F0, F1. So they had a 4-bit truth table, and they started diligently filling that out. And you can see I have to go 32 down and 32 ones, and I'll have to do this. So 64, I'll have to fill in a 64-bit truth table. And this isn't exactly helpful for what we need. This will give us every possible output that F could be in every scenario, given I, A, and F. But it isn't really what the lab's asking us. It's not saying, what is F in every situation. Really, it's saying we need to define some kind of a function given I, a function of A and B. So rather than this table, which will give us all of the values of any of the function, we want a table that looks a little more like this. Hold on. we want a table that looks a little more like this. So f, in fact, we'll just call it f of a comma b, like that. So we're told basically really easily in the lab what all of these values should be. So let's just go through it. We say I is 0, 0. Then f is a bitwise ANDing of our inputs. So we'll go ahead and write that out in our truth table. We'll say 0, 0. And we're doing bitwise ANDing of our inputs. So f. So our f of a and b is equal to a and b. Okay. And then 0, 1, this is an ORing, A or B. Well, I guess I'll use Boolean algebra that I use there. So A or B. And then 1, 0, this is A equals B. And then 1, 1, we're told in the lab that 1, 1 is the complement of A. Yeah, just the complement of A. So that's easy enough. So we'll just say not the tilde A. Okay, so basically this is what we're asked here. So we've got this truth table for all the values of I, and we have the different functions that each of those values represent. That's what we need to know. So now the question is, how are we going to make a choice in hardware? So if we were thinking about this in software, if this was C or Java or some other language, we might use an if-else statement or a case statement to be able to say, if I is this, then F is that. And if I is this, then F is that, and so on and so forth. How do we do that in hardware? How do we perform a hardware if statement? Well, the answer to that question is called a multiplexer. And to understand what a multiplexer is, I'm going to just go to the book for a minute. This is on page 62 of your book, chapter 2. And it gives you a circuit here, which is it is the circuit of a truth table. So if we look at, it is the circuit of a multiplexer. So we look at the truth table, we see, okay, given S is our selector. It's the same thing as I. S will represent I in our circuit, and then in the book they call it S. In this case, they go through here and they say, okay, so if S is 0, then X1 is 0 and X2 is 0, then F will be 0. If S is 0 and X1 is 0 and X2 is 1, then F will still be 0. And if we look for a pattern, we'll see that we'll have 0, 1, 0, we'll have 1 here. So if we have X1 being 1 and S being 0, then we get X1. And if we have, so when we have S being 0 and X1 being 0, we have F being 0. Oh, okay. So when we have S being 0, we have X1 being 0, we have F being 0. When we have S being 0 and X1 being 0, it doesn't matter what X2 is, we still have 0. When S is 0 and X1 is 1 and X2 is 0, now we get 1. It doesn't matter what X2 is, we're always going to get 1 so long as X1 is 1 and S is 0. We switch to S being 1 and we get the same kind of pattern where now we're just selecting for X2. So if S is 1, X2 is 1, then we get 1. If S is 1, X2 is 0, we get 0, and so on. So what we're seeing is that S is selecting between x1 and x2. And a simpler truth table representation of that is exactly what we have right here, x1 and x2. So the graphical symbol for this kind of a circuit looks like this. It's like a trapezoid shape, and the inputs go on the left here, the output goes on the right, and the selector goes on the top or sometimes on the bottom. I've seen it both ways. So this is a 1-bit selector. In other words, S only has 1 bit. So this is what we call a 2-to-1 multiplexer. It takes 2 inputs and it selects one based on S. And this is our design for it. And to understand how that design works, I'm going to open up a little app called Logically that I use. It's not a powerful app by any means, but it's nice for demonstrations. So I'm going to just make this circuit here with 2 AND gates. And a NOT gate between them. I'm going to rotate counterclockwise. And I'll have a couple of switches here to represent our selector. And then one to represent x1 and one to represent x2. Okay, so I'll go ahead and connect this just as they have it right here. Yeah, okay, so we have our selector bit. We'll call that S. Goes in right there. And also right here. Okay, and then we'll rearrange these. I'm going to move my selector so maybe I'm not. All right, then this will be x1, and this will be x2. I'll go ahead and add some labels so that we can see what we're talking about. So this is S, and this is x1, and this is x2. All right, and it's a little bit of it's a little bit not, I mean, it's a little ugly because, like I said, this is not a very powerful tool, but we're going to go with it and just bear with me. So now the last thing we need is an OR gate. And connect, and connect. And to see an output, we'll just use a little light bulb here to see what happens. All right, so let's go ahead and start flipping some switches. So we'll turn X1 on, turn X2 on. And what we see, or we'll turn X2 off. So right now, S is selected for off. So if we switch that, now what's happening is S is on, which means that we're now selecting for, you can follow the path, this NOT gate here basically turns this S on signal to be off. So when it's ANDed, X1 doesn't get through that AND gate. Then we come through here, S is on, and so whatever's on X2 gets through the AND gate. Because X2 is off, the AND gate remains off. So now I can turn the light on and off by just switching between X2 and X1. And I'll give you guys a minute just to follow those lines and see if you can kind of make sense of what's happening. We have our S here. S is off. So when it goes to the NOT gate, it gets turned on. X1 is on. So when it's on and on, they go through the AND gate and it turns on. And if I turn X1 off, then the light turns off. If I turn X2 on, it doesn't change anything because we're only selecting for X1. If I switch, now the light is on because X2 is now on. And you can see S goes through the AND gate without being inverted. X2 goes through the AND gate because X2 is on. It goes through the OR gate and the light is on. So this is a multiplexer. It allows you to select between two inputs. Now, we want to expand this for our lab. We want, because we have a 2-bit selector, then what we want is a 4-to-1 multiplexer. So let's see about how we could design that. The first thing to do is to look at a truth table for a 4-to-1 multiplexer. So let's go ahead and create one of those. Okay, so I'm going to go I0, I1, and then I will have my inputs. I will call this F0, F1, F2, F3, and that's all of them. That's 4, 0, 3. Okay. And what I want to make clear here is that these are not positions, these are not bit positions of an F. These are meant to represent 4 different functions: F0, F1, F2, F3. In fact, I can make that even more clear by just calling this F, G, Y, Z. Okay, so these are 4 different functions now: F, G, Y, and Z. So let's go through, and when I put a 1 in one of these columns, it means that that's what we will be selecting, is that function. So let's go through and write out this truth table. So we'll start with 0, 0, 1, 1, and then go 0, 1, 0, 1. All right. So we want to basically say that for each of these unique inputs, we select a different function. So we'll go through here and just fill that out. We'll say 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. Okay, and we end up with this diagonal pattern here. That for every one of these unique inputs, we have a unique output. It gives us this diagonal pattern. That's a pretty good telltale sign that what we're dealing with is a multiplexer when we get that diagonal pattern. So what we need is we're going to need 2 negations, because if we look at this, we need to be able to select a different function when I0 is 0 and when I1 is 0. So we need a negation for both I0 and I1. And so let's go ahead and start trying to design this truth table in our tool. So we'll go ahead and delete all of this. I'll just go new. close that one. Don't save it. All right, we're going to have to zoom out for this one. All right, so let's start. We know that we're going to have inputs for I0 and I1. So we'll have our I0, I1 inputs. Okay, we'll go ahead and label those. All right, and now we'll have our different functions that we will just represent here as switches. Now, I want to be clear that they can be any function. They can be as complex or as simple as need be. For this demonstration, I'm just going to represent them as, or I'll represent them as push buttons because that could be fun. So here are our 4 functions. Now we know that we need 2 inverters. So let's go ahead and add those. Let's continue looking at our circuit for a moment, or our truth table. So when we're going to need to AND these 2 inputs together, so let's go ahead and create 2 AND gates. Actually, I think we're going to need, see, an AND gate here for 0, 0. Yeah, let's see. I think, let's start with 2 and see where we get. All right. I think we're going to need, actually, I know we're going to need more than that. So this is going to be a 3-input AND gate because we'll need to AND for S as well, or rather I, because I called it I. And it's actually a 4-input AND gate because we'll need to AND for I0 and I1. Okay, so we're going to need that. And we're going to need another 4-input AND gate over here. All right. So we will go ahead and connect our switches to our buffers, or not our buffers, I'm sorry, our inverters. Oh, this guy here, like that. Okay. So here's our selectors, there's our inverters. So when we want to say I1 is 0 and I0 is 0, we want to select for F. So that means we'll want to connect this inverter and that inverter and, oh, this only needs to be a 3-input AND gate because we're representing our functions with just push buttons and F. All right, so there's that one. Now, when we have 0 and 1, we want to select for G. So we have our I0 being 0. This is going to get messy. One. So yeah, we're going to need 4 of these AND gates, 1 for each input. one for each function. Okay, then we're going to select for G. Okay, and we're going to repeat the process. So, 3, same thing. In this case, we're dealing with 1 and 0. So we want to grab from I0 and not I1. All right, you guys. So this is what happens when you try and build these circuits on the fly. This is just getting real messy. But hopefully you're following along what this, basically the pattern that we're seeing here. And then finally we have 1 and 1. Come on, connect. 1 and 1. And make that a 3 input. And for our last one here. All right, that's a great big mess, but it will illustrate our point, and thankfully the highlighting will help. So we'll drop an OR gate here. This is going to be a 4 input OR gate and a light bulb to see what's happening. This is, by the way, what we call sum of products. We have an OR gate with a bunch of AND gates going into it. This is a very standard form for logic simplification. All right. So with both of these off, I should be able to push this button and turn the light bulb on if I've done everything correctly. Hey, look at that. And none of these buttons should do anything. And they don't. So 0, 1, we should now be able to turn on this light. There we go. Okay. 1, 0. Should now be able to turn on this light. Very nice. Okay. And 1, 1, we should now be able to turn on this light. All right. So 2 inverters, 4 AND gates, and an OR gate, and we get a 2-to-1 multiplexer. Now, this is the same pattern that you're going to follow for as you expand your multiplexers. So if you wanted a 3-to-1 multiplexer, you'd add a 3rd switch, and then you'd have 8 push buttons, and you'd connect 8 AND gates. 4, you'd have 4 switches, so you'd have a 4-to-1, so you'd have 4 switches, 16 buttons, and a light bulb. No, sorry. You'd have so 4 switches would be a 16-to-1 multiplexer. So 2 switches is a 4-to-1 multiplexer because it takes 4 inputs and brings it to 1. 3 switches is an 8-to-1 multiplexer because it takes 8 inputs and brings it to 1. So the amount of switches you need is the log 2 of the number of inputs. Or to put it another way, the number of inputs you need is the number of switches you have, 2 to the number of switches you have. So either way you want to think about it, if I have 2 switches, I get 4 inputs. If I have 3 switches, I get 8 inputs. If I need 16 inputs, then I have to have 4 switches. Any way you want to look at that. But this is the basics of a multiplexer, and you can see how using just some simple AND gates and a couple of inverters, we can now make essentially a hardware case select as large as we want. So that's what this lab is all about, is helping you understand what a multiplexer is, how to make one, and how to use it. So going back now, we figured out our multiplexer equation, our circuit. We have our truth table. Now the last thing to do is to design it in Verilog. So I'm going to open up Visual Studio Code here because I'm on my Mac. So I'm not using Quartus right now, but I can still code inside of Visual Studio Code. Looks like if I expand it, you won't be able to see the webcam. Not that that's the worst thing in the world, but just make this a little smaller here. Okay, so the first thing the lab tells us is that we can't use the built-in Quartus multiplexers. So we had to design our own. We just did the circuit for that, so it shouldn't be too hard. Let's go ahead and get started. Everything inside of Quartus, it begins with a module. Everything exists inside a module. A module, I like to think of it, the best way to think about it is, for me, is like an integrated circuit. It's sort of a black box. Inputs come in, outputs go out. What happens in between is only known to the circuit and those that design it. So that's kind of how a module is going to be. We're going to put some code in there that will define some hardware behavior, and based on that, things will happen. So I think it'll make a little more sense as we go along. I'm going to go ahead and call this like a Mux, and I'm going to start giving it some ports. Now the way to define ports is very simple. We're going to say input, and we want a selector. So you can call this I, you can call this S, you can call it kind of whatever you want. And we're defining a 4-to-1 multiplexer here. So let's say input S, or input wire. And then I want to say, because I want it to be a 4-input or 4-bit multiplexer, I want to say that my selector gets 2 bits. Rather than having 2 inputs, S0 and S1, I can say that I have a vector input, and I define it like this. So 1:0 means that I have a wire that is actually a bus that has 2 bits on it that I can individually select. So it's like a vector or an array if you're in C. But logically, or not logically, but topologically, it is a bus since we're defining hardware. All right, input wire, I will call this S, or I'll call it select. I like to be explicit, I'll call it select. Then I'm going to say input wire, and now I have 4, I'm sorry, I'm losing my train of thought. I have 4 possible selections. So these will I'll just leave as 1 bit, and I'll say, I'll call these X1, input wire X2, input wire X3, and input wire X4. Okay, so there's my module with its inputs. Oh, and it needs an output. Of course it needs an output. And I'll say output wire F for the function. All right. Now, we're told in the lab, and this is where I made a mistake, because as I was helping some students through it, I helped them design it the way that I would have designed it, using behavioral features of Verilog, using an always statement and a case block statement. But the lab, I didn't see this before, actually says where is it? It's down here. In this lab, you are not allowed to use behavioral constructs such as always statements for this design. We will do that in a later lab. I didn't see that. In fact, I still had to look for it to see it just now. So I'm going to take you through the ways that they want you to do it instead. Schematic entry I will do in class is going to be the easiest way for you to see and to understand the schematic entries if I just show you in class. But I'll take you to the Verilog. So the first one they mentioned here is structural Verilog. So what they mean by this is that you will use and or not XOR gates explicitly. So in structural Verilog, we explicitly tell the compiler what gates we're trying to synthesize. So it looks something like this. We have an and or whatever type of gate we want, not, etc. And then we have the output and then the inputs. So input, 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 etc. To do this correctly, we need to make some intermediary wires. These are wires that are not inputs, they're not outputs, they exist inside the module, and they are not accessible outside of it. So let's create a few. We know that we're going to need to negate our select bits from our previous example that we did. So let's go and make a couple of wires to hold the negation. So let's say wire n select 0 and select 1. And we also know that we're going to need 4 AND gates for our ANDing of the selects with the various inputs. So let's call those F0, F1, F2, and F3. All right, so these are our intermediary wires that we're going to need. These are going to hold the outputs that will be passed along to the various gates. So we'll start by defining what our n select 0 and n select 1 are. And those are the negation of our select bits. So we will do not n select 0. That's where the output lives. And then select 0. So what we've done here is we've said the negation of select 0 exists on the wire n select 0. We've now connected those. So we'll do the same thing for n select 1. Okay. And we'll do the same thing for, well, we're not going to invert now. We need our AND gates. So we have our 2 NOT gates, and we have access to the original input, so we'll be okay there. Now we need our AND gates. And so if we think back to our truth table, we remember that when we had 0, 0, then we had F0. So we want to AND n select 0 and n select 1 and F0. And that literally says, oh, and then we want to put that on an output. Yeah, that's how I have it written backwards here, sorry. Wait, no, I don't. I want to say F0, and then I want to put that on an output. So we'll need a wire. Oh, I got confused. I'm sorry. X1 is our input, and then F0 is our output. There we go. So now I'm saying that if select 0 is false and select 1 is false, or rather if the negation of them are true, then and x1 is true, put whatever that value is on f0. So if any one of these is 0, then f0 gets 0. If all of these are 1, then f0 gets 1. Okay? And then I'm going to repeat this process for my entire truth table. So, and I'm going to say the output is f1. I want 0, 1 as the next option. So, and select 0 and select 1. And this should be x2 and f2 and select 0. No, it's 1, 0 after that. So it's select 0 and select 1. So 0, 1, and that's x3. And then finally, like that. All right. So last thing I need to do is add f0, f1, f2, and f3 to an OR gate. And I'll assign that to my output f. So I'll say OR f, and then f0, f1, f2, and f3. All right. And that is a multiplexer using structural or gate level modeling. All right, let's see what the other modeling types look like. Let's go to the lab here. We want functional modeling. Okay, this is one I'm a little more familiar with. So this is using assign statements. So the other value that they want to use is assign statements. So let's create another module. I will new file here, and I'll say call this Mux functional. Okay. Module. One thing I want to point out is that your module name should mimic your file name. And if it doesn't do that, all sorts of weird things can happen. So if you can actually define multiple modules in a single Verilog file, though I don't usually recommend it unless you have a lot of small modules. But one of them at least has to have the same name as the file. Okay. So same thing here. We want our select, our input wire select, and it is a 2-bit wire. So, and then we want our 4 inputs. Okay, and these are also all input wires. All right, and we need our output. F. no semicolon. All right. So now that we have our inputs and our outputs, we are going to use functional level modeling. And functional level modeling is one level of abstraction over gate level modeling. So instead of defining all of the individual gates, we're going to define logic equations and allow the compiler to create the appropriate gates. So the way we do this is we'll say assign, and we can let's make some intermediate wires, but we don't need quite as many. So we'll say wire, I'll keep the F0, F1, F2, F3, but I won't need the end selects. So do those. Okay, so let's go ahead and assign F0 equals, and what does F0 equal? It equals not, you can use the exclamation mark, you can use the tilde. The difference here is that the tilde is a bitwise negation, and the exclamation mark is a logical negation. In the case of select, we actually want the bitwise negation, because we want to say not select, which means that if select is 0, 0, so if not select is equal to tick B 1, 1. Now I'm going to explain this syntax here. This 2 defines how many bits we're going to have on this side here. The apostrophe is just part of the syntax, and the B says we're defining this value in binary. So in general, the syntax is N apostrophe B and then XXX dot 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 up to N. So however many ends you have, that's how many bits you need to specify in 0 or 1. There are some other syntaxes you can use. For example, you could do 2 tick D, and instead of specifying the bits specifically, I could say 3, and the compiler will turn that into a 2-bit binary representation of the number, decimal number 3. So those are the two I use. There's also, N tick H for hex, and I think there's one for octal as well. But most of the time I use B or D, just depending on what's easier. All right. So we're saying that if the negation of select is equal to the binary number 1, 1, sorry, and I'll put these all in an AND gate, so I'm going to AND that, one AND, with, in this case, X0. Okay, and then assign F1 equals not select. I'm going to put this in parentheses as well to be explicit. Is equal to tick B1, 0 and X1. And I'm going to repeat that process. You could also, if you didn't want to do the equals, you could also say not select. You could do any combination of gates. Really, you could do like an XOR, any combination of gates that works for you. The equality operator is just, it's simple, and Verilog will the compiler is going to synthesize that in as simple way as possible for you. So that's how I like to do it. But this is what we call functional modeling. Instead of defining the gates themselves, we're now defining a equation. What is the function of F0 and F1? So we're actually defining functions and putting those values into F0 and F1, and then we can assign F equals to F0 or F1 or F2, etc. So that's functional modeling. So those are the two versions that the lab asks you to use. If I took you through behavioral modeling, I'm sorry. It is the way that I would use if I was given this assignment today. I missed that one line that says not to use it that way. But if you can do it in behavioral, you can do it in structural and functional without any problem. So, yeah, let me know if there are any questions. Please reach out to me, email, Discord. I'm going to be posting my office hours soon so that you'll have those as well.